Section 9.3, Linear Systems with 3 Variables. In this section, we'll solve systems of 3 equations with 3 variables, and we'll identify inconsistent and dependent systems with 3 variables. So solving a system with 3 variables is not difficult, but it requires 3 things: neatness, a plan, and precision. And I can already hear some of you saying to yourself, I'm not neat, I'm not precise. This is going to be super frustrating if you're not neat and precise. So just try to maybe be a little neater and a little more precise than you usually are, because in this type of problem, one little mistake along the way and the whole thing's going to be wrong. So just putting that out there to something that you might want to think about. All right, so when solving a system, you can make the following moves. You can interchange the order of the equations. You can multiply both sides of an equation by a constant, as long as it's not 0. And you can add a multiple of one equation to another equation, and any of these moves will not affect the solution. Your goal is to use one of the equations and one of the variables to reduce the system to 2 equations with 2 variables or less. And to do this, you need to make a plan and stick to it. All right, so if you've never done this before, I'll try to help you figure out how to make your plan, because that's probably the hardest part. So here's our first example. We're going to solve this system. So my plan is going to be to take my first equation, and I'm going to use it to eliminate y in the other 2 equations. That's my plan. My plan is to eliminate y using equation 1, the first one in the list. So how do I do that? All right, well, let me clear out this circle so you can see better. I'm going to want to get rid of y in our second equation. And to get rid of y in our second equation, I need the first equation to have a coefficient of 4. So I'm going to multiply both sides of this equation by 4. 4x plus 4y plus 4z is equal to 8. And our second equation is 6x minus 4y plus 5z is equal to 31. And the reason I did that is so that when I add these equations together and get 10x plus 9z is equal to 39, notice that my y has been eliminated. So second equation is done. All right, so far I have done the second equation. Now I want to do the same thing to the third equation. So notice that here I have a positive 2. So what I would like is to use a negative 2 to eliminate it. So I'm going to multiply both sides of this first equation by negative 2. That gives me negative 2x minus 2y minus 2z is equal to negative 4. The third equation is 5x plus 2y plus 2z is equal to 13. And we'll add these together, giving us 3x. Oh, we got an added bonus. Not only was y eliminated, z was also eliminated. So we have 3x is equal to 9. Now, normally at this point, what we have are 2 equations, our first result and our second result. And usually we have 2 equations with 2 variables in them, which then we would approach like we did in section 9.1, solve the system. We lucked out in this one with this approach because notice that the second equation only has 1 variable, so we can automatically go ahead and solve that. So if we solve that, now we know that x is equal to 3. Once I know that x is equal to 3, I can come back here to this equation that only has 2 variables in it and substitute 3. 30, 10 times 3, plus 9z is equal to 39. Subtracting 30 from each side, we have 9z is equal to 30. 9z is equal to 9. In other words, now we know that z is equal to 1. Now that we know x and z, we can go back to any of the original equations and solve for our last variable. So I'm going to come here to this first equation. I know x is 3. I don't know what y is. I know z is 1 is equal to 2. In other words, 4 plus y is equal to 2. In other words, y is equal to negative 2. And so we write our solution usually as an ordered triple. So x is 3, y is negative 2, and z is 1. Excuse me. Now, had we picked a different plan and a different variable, we may not have lucked out like that. There's no way of predicting in advance what's going to be the easiest approach. We just happen to luck out and get an easy one that time. Here, let's try another one. All right, so I need to make a plan. So I think what I'm going to do is I'm going to use the first equation, or actually I think what I'm going to use the second equation, and I'm going to use it to get rid of x. The reason I picked the second equation is because x is negative there, and I won't have to multiply by any negative numbers to do that. All right, so let's take a look. So let's take a look at the first equation. The first equation has a positive x, and to get rid of it, I would need a negative x, which I already have in the second equation. So I'm going to take my second equation, x plus 3y minus z is equal to negative 6, and I don't have to multiply it by anything to get rid of x in the first equation. So the first equation is x minus 2y plus 3z is equal to 9. We're going to add these together, giving us y plus 2z is equal to 3. Now, I need to keep track of that equation because I know I'm going to need to put it together with my next result. So sometimes what I do is I circle it, or I make sure that I can find it later. All right, so first equation done. Now let's take a look at the third equation. To get rid of this x, I would need a negative 2. So I'm going to multiply both sides of the second equation, the one I'm using. I'm going to multiply both sides of this equation by negative 2. Excuse me, just by 2. That's why I picked it, so I wouldn't have to use the negative. All right, so I'm going to multiply both sides of this equation by 2. Let's see what we have. Negative 2x plus 6y minus 2z is equal to negative 12. And the third equation is 2x minus 5y plus 5z is equal to 17. And we're going to add these together. We have y plus 3z is equal to 5. And so here's our second result. So what I need to do now is I need to take these two equations, put them together, and solve that system. So my system now that's been reduced to equations is y plus 2z is equal to 3, and y plus 3z is equal to 5. So to solve this, I'm going to multiply this first equation by negative 1. Negative y minus 2z is equal to negative 3. Y plus 3z is equal to 5. Let's add these equations together. Y has just been eliminated, so we have z is equal to 2. We stay here in an equation that has two variables, so I'm just going to put that right in there. Y plus 3 times 2 is 6. Y plus 6 is equal to 5. And now I know that y is equal to negative 1. Once I have two solutions, I can come back to the original equations. Any of the original equations will be fine, and plug these numbers in. So I'm going to use the first equation. X, negative 2 times y, negative 2 times negative 1 is plus 2. 3 times z, 3 times 2 is 6, is equal to 9. X plus 8 is equal to 9, and so x is equal to 1. So our solution is x is equal to 1, y is equal to negative 1, and z is equal to 2. And if we wanted to check that, we would just plug those values into every equation of the originals and make sure that they worked. Do you have always have a solution with 3 equations? And the answer is no. You can have inconsistent equations. So I'm going to give you a minute to think about this, and there'll be a quiz question. How do you recognize a system is inconsistent? When you're solving, what tells you that a system is inconsistent, meaning it has no solution? Okay, so it's exactly the same with 3 variables. What you're going to get when you're solving and you've made your plan and you're executing your plan, you come up with a situation where you have no variables left and a false statement. Like you were solving and you came up with something like 0 equals 2, for example. What that means graphically, when you have a solution, an equation that has 3 variables in it, the graph of the three variable equation is a plane. And so what you have then are 3 planes that do not intersect in a single point. Either they're all parallel to each other, or you might have this situation or this situation where they intersect in lines, but not at a single point. And so that would be what geometrically it means to have no solution. Okay. How do you recognize a dependent system? Well, if you remembered how you recognize the inconsistent one, then you probably recognize that with the dependent system, you're solving and you come up with a true statement, but all the variables have been eliminated.